Welcome to this session. In this session, we will be dealing with integral equations, an important topic for CSIR NET examination. It will surely help you to collect two questions, one from 4.75 and another one from 3 marks. Okay. Not most important, but for those who are preparing for Unit 3, they must do integral equations just to grab more marks from this side. Okay. So let's see what are integral equations basically. Okay. So an integral equation is nothing but, okay, so let me write down. Okay. An integral equation is an equation in which a known function appears under one or more than one integral sign. What do I mean by this? So let's say its general form looks like, first let me take one example and then I'll tell you its general form. So let's say I have an equation, say y of x looking like x square plus some 2 times integral from 0 to 1 I'm saying, and then I have e power x minus t and then y of t dt. Fine. This is simply one example, and here I do not know what is my y. Okay, this y here is my unknown function, because I cannot say this y of x as a function of x completely, because here in the next term I have here y of t dt. So unless and until I know what is this y of t, okay, I cannot say that I know particularly this equation. So here y of x is unknown. Now let me write down its general form so that I can tell you in more detail what this y and this x, e power x minus t and these things are. Okay. So let me write down the most general form. So in case we write the most general form, the general form looks like this. You have here alpha of x, then y of x equal to some f of x, function of x, plus some lambda times this domain omega in k of xt, then y of t dt. Okay. Here you need to be very sure that this y of x is unknown. Okay, alpha, f, and this k, okay, are known functions. These are your known functions. Means here your f of x here is x square. Here alpha of x is nothing, so I can take it 1. So alpha of x is 1. Okay, it is even known, and even lambda is known. So that's your parameter. So lambda is a non-zero parameter. Non-zero parameter. It may be real, it may be complex. That does not matter. Okay, it may be real or it may be complex. Fine. And this k is nothing but kernel of this integral equation. Kernel. Let me change the page. K of xt is nothing but kernel of the integral equation. Kernel of the integral equation. And this omega is nothing but the, you say limit or domain of integration, because here there will be two types, limit or I'll be saying domain in fact. Okay, of the integration. I'm writing here omega because omega will stand for two things. If it is variable and then constants. So based on these two things, these integral equations are further classified into two types. Okay, one is called Voltaire and another one is Fredholm. So we will be dealing with this. But before that, let me classify linear and non-linear integral equations first, and then we'll be dealing with these basic types. Okay. So let's write down linear. So you got two categories. linear and non-linear. Yeah. If it is linear, then we will categorize it further. Fine. So it will come under two categories. One is Volterra and another one is Freedom. Yeah. If it is non-linear, there is no need to classify because most of the time we do not have easy method to solve such kind of integral equations. Okay. But for the time, we have to stick with the linear equations, linear integral equations, Volterra and Freedom only. Okay. So would I say that integral equation is linear? Okay. So let me write down the definition here. So those who have studied even the basic algebra, they must be able to tell this. Linear is nothing but here. So let me write down in fact. And integral equation is linear if and only if linear operations are performed. Linear operations are performed. Yeah. And linear operations are performed on whom? So you have to mention this. So I can say that if and only if linear operations are performed in it, okay, upon the unknown function. This word is very important. Upon the unknown function. Okay. That means if I can, we know the definition of linear transformation, that's same as this one. So I have to say this, then I'll say, let's say y1 of x. So c1 times y1 of x plus c2 times y2 of x. If you can write it down like this, c1 times L of y1 of x plus c2 times L of y2 of x, just for checking the linearity. So far you must have done linear transformation. So whenever you have to check something is a linear transformation, this is what you have done. Let's say you have given t of xy equal to some x plus y. So to check this linear transformation, you must have done this alpha x plus beta y. Okay, this is what you have done. The same thing that we are doing here. Okay, just in the form of here we have got unknown functions. So I'm performing on y1 of x and y2 of x. I'll be performing and checking it. Correct. Now let me categorize them further. Okay. So we come for Volterra and Freedom. Now let's say, so they are categorized on the basis of limit of integration. Okay, limit of integration. I'm talking about this quantity. Okay, here there were constants 0 and 1. So this is another type. But if I have a limit like this, say 0 to x, then this will be Volterra. Now let me mention the types and then I'll go further. So first type will be, okay, let me write down here, integral equations in short, and then they are further categorized into Volterra and Freedom. This is not Fredholm. This is not Fredol. It's Freedom. Now let's see. In the Volterra, you have the same thing. Let's say alpha of x into y of x equal to some f of x plus lambda times some a to x. Okay. Then k of xt to y of t dt. Okay. And in Freedom, you have, so just by a mere looking at this quantity, you can easily make out the thing that when an integral equation will be Volterra and when it will be Freedom. This is there is no space, so it's just k of xt into y of t dt. Okay. Now, if you look at the limits very carefully, then you see that limit here is a variable. Okay, a to x I have, and here they are totally constants. Okay, here these two things are totally constant, basically. Okay, so you can say here your omega is nothing but from a to x, and here your omega is from a to b. All right. Now this quantity will be Volterra. Okay, when you have limit of the integration as one variable, Okay, it's not necessarily from a to x. It can have function from both ends. Okay, that will be Volterra. Okay, and when I have all the constant limit from a to b, like say 0 to 1, -1 to 4, anything, then it will be Freedom. Okay, now further they are again classified. So let me classify them further. Oh, sorry, this is, yeah, they are further classified into two types. Okay, first kind and second kind. First kind, second kind. Same thing here. Freedom we also describe into two parts further. Again, first kind and second kind. Few authors mention even the third kind. Okay, but here in this case we will keep it for some time as option, because mostly there are chances of confusion. So I'll not be getting into the third kind, but while solving the problem, I'll mention the use of third kind and how to solve this. But for the time, we will stick to the first kind and second kind only. Okay, based on Volterra and Freedom both. Now let's see what are its first kind and second kind. Okay. And of course, this let me mention this thing even. First kind, second kind. Again, in first kind, second kind, there will be two more cases: homogeneous and non-homogeneous. So I'm sure about it. When I say homogeneous, okay, easily. But if I have to check the homogeneity, then homogeneity will depend upon f of x. Okay, if my f of x is 0, then this integral equation will be basically homogeneous. Okay, this is what you have done. And if you cannot relate it, then just simply remember a differential equation like this. Let's say y dash plus some constant times y equal to some r of x. Okay, this is a non-homogeneous second order differential equation. Okay, now when this r of x was 0, we said that this is a homogeneous, and when r of x is non-zero, then it will be non-homogeneous basically. Okay, solution of a non-homogeneous equation is never trivial. Okay, we cannot have a zero solution for this because it will not satisfy. Okay, then in the same lines, we have even Volterra and Freedom integral equations as well. So here in this case, it will solely depend upon f of x, whether it is homogeneous or non-homogeneous, and this first kind and second kind will depend upon this quantity. Okay. Now let us see what it will be. And see, the idea here remains same. Okay, for the first kind and second kind, idea here remains same. Only this limit will make the difference. These limits are going to make the difference and nothing else. Else, first kind and second kind for both these equations remains same. So you don't have to worry about that. You have four types. You don't have to worry. Okay. It's that simple. Let me take one. Yeah. So here I'll be saying what is first kind basically. First kind, and here I'll be mentioning second kind. And then there are some singular integrals that I'll mentioning after I complete this first kind and second kind. So let's deal with this first kind and second kind. Yeah. So in first kind, let me first homogeneous thing. Okay, it will be homogeneous when your f of x is 0. Okay, and it will be non-homogeneous when f of x is non-zero. The same thing follows here as well. Same thing follows here. So just let me write down this and write down here. In fact, same thing follows here. See, I'm writing first kind and second kind. So this first part is for Volterra and second part is for Freedom. Everything will remain same. So I'm not classifying them in terms of especially particularly for Volterra and particularly for Freedom. Okay, because these things are same for both the types of equations. So we will be considering only two parts, first kind and second kind. So homogeneous and non-homogeneous remains same, or else just for your confusion. So you must have confusion. Let me erase this. Fine, this is seriously not needed. I'll mention at the last stage. This homogeneous and non-homogeneous. But before that, let me mention this first kind. Yeah. let's say first kind, everything depends upon alpha. Okay, so if alpha of x is 0, if this alpha of x is 0, just have a look at this. If alpha of x is 0, that means this entire quantity is 0. Okay, so means I can express this f of x as some function of y independent. Okay, so in that case I'll be getting, okay, so you write here the equation involves, the equation involves unknown function y of t under the integral sign. So if it is 0, then I'll say 0 equal to some f of x plus lambda times integral a to x, or in fact, let me not write down a to x, just write down omega so that you get the flavor. Okay, that it is for both these things. Okay. Y of t dt. I can easily express this f of x equal to, okay, you may write here lambda, you may not write here, you may write here minus lambda, that will be taken care of, but its general type will be like this. Okay. This is your first kind integral equation. Yeah, first kind integral equation. Now, when I talk about second kind, then here it will be alpha of x will not be 0 but constant. But a constant. That means what? Y of x will remain into the picture, but let's say alpha of x is non-zero. When I say constant, constant means what? It can be non-constant as well, but it will be a variable function. Let us say I have this x square times y of x, okay, equal to some sine x plus some c times, and then this integral, this entire quantity follows ax t y of t dt. See, even alpha of x is non-zero here, but this is not constant. Okay, this is a variable. So here, especially I'm saying constant. That means this is not x square, but some constant, 2, 3, anything. Okay, so such types are known as second kind. Now let us see. Alpha of x is non-zero, then integral equation is called second kind. Second kind integral equation. Okay, second kind integral equation. And now the third type, which I had mentioned, third kind. Okay, everything will depend upon alpha. That's what I mentioned. Everything will depend upon this alpha thing. This f of x will describe only the homogeneity and non-homogeneity. This alpha of x will describe its first kind and second kind. When this alpha of x is non-zero but variable, okay, then this type will come into the third kind. Okay, third kind. This is not mostly dealt, but still. Third kind is what? You have alpha of x is non-zero, but here it will be non-constant as well. It will be non-constant even. Okay, it will be some variable. Okay, then the equation will be your third kind. Okay, so let me write down the example as well. So let me write down here x square and then y of x equal to some f of x plus lambda times omega kxt yt dt. Okay, please make a note here. Everything I'm following the same thing. So I'm sure you must have got the flavor now for first kind and second kind and third kind. Okay, this kind of such kind of integral equations are not mostly there in the picture, but these two appear frequently. And in CSIR examination, you will always find a question based on these two things for sure, and that is damn fixed. Okay. So if you are prepared with Unit 1 and Unit 2, and if you want Unit 3 for benefit, then this would be the right thing for you. Okay, in CSIR NET. Earlier, this was there in GATE examination, but later they dropped it. But these things work very, very nicely in higher field. So since we are ready with the things first kind and second kind under our belt, we will now deal with the types, and now everything will depend upon the classification of kernels. See, we have discussed about f of x and this alpha of x. Now the things come about kxt. This is called as kernel. Okay. So here we can follow for 3 to 4 things. Okay, Fredholm integral equation of first kind, homogeneous, non-homogeneous, uh, Volterra integral equation of second kind, homogeneous or non-homogeneous. Okay, or second kind, first kind. These things will come, but let me first introduce kernel. Okay, kxt. Okay, this is again is of two type. Okay, here for the time we will consider only two type. Because there are many skew symmetric kernel, symmetric kernel, then degenerate kernel, separable kernel, inseparable kernel, convolution type kernel. There are many, but its main classification is three. Let me classify them. One is called degenerate, or we also call it separable kernel. Separable kernel. Sometimes questions are framed from this topic. Okay, they will ask you which of the following is a degenerate or separable kernel. Okay, and then comes your symmetric or skew symmetric, symmetric or skew symmetric kernel, and then comes your convolution type kernel. Please, my friends, forgive the unwanted sound. Okay. This is Ganpati time, so we can expect such things in our neighborhood. I'm not recording the lecture in the studio. It's my home. So please forgive these things. I'm sure you can manage. Okay. Now, let's go. So degenerate or separable kernel. What is this degenerate or separable kernel? Though this word looks little less familiar, but we are familiar with separable kind of thing. Okay. That means what? If, now let me write down the explanation. Just give me 1 minute. It was necessary to close the window. So let's go for degenerate kernel. Here, when you express, you can express your kernel, say k of xt, some function of say I equal to 1 to n alpha I of x into some beta I of t. It was k of xt. So if I can express them, okay, as completely a function of x and a function of t, then my kernel in that case will be separable kernel. Okay, completely as a function of x and completely as a function of t. Okay, let's say example, you have here e power x minus t. Okay, this I can write down e power x into e power minus t. So here this is completely a function of x, and here this is completely a function of t. So in that case, this kernel is a separable kernel. Okay, and this is again a very important thing. X minus t, I'm not playing into the game that x minus t is convolution. Here I'll explain this again. This x minus t is nothing but, in fact, whenever your kxt is of this type, f of x minus t, and such kind of kernels are known as convolution kernel. Okay, f of x minus t. Let's say example, you have sine of x minus t. Okay, sine of x minus t, or you can even take e power x minus t. This is again convolution type, though it is separable here. So it's convolution type separable kernel. Okay, you can combine both. Okay, and here symmetric in this case. So for symmetric, you must have seen this k of xt. Okay, k of xt must be equal to k of tx. So in that case, your kernel will be symmetric. Okay, and one more thing, this will be k of tx bar. Okay, this bar stands for complex conjugate. Okay, complex conjugate. In that case, our kernel will be symmetric. K of xt, if I can write down this, k of tx bar, if they are equal, then my kernel will be symmetric kernel. Okay. In the case, if I have minus sign, then it will be skew symmetric, just like our matrix. Okay, so these are basic types of all these things. First we did integral equations. They are mainly classified into linear and non-linear. When it is linear, we went to classify them into further categories like Volterra and Freedom. And when it is non-linear, we did not classify them. Okay. When it is linear, again we got two types, Volterra and Freedom. In that Volterra and Freedom, we have first kind and second kind based on homogeneity and non-homogeneity, based on alpha of x. Then we got first kind, second kind, and third kind. Now, since we are ready with few concepts under our belt, it is now feasible to solve some problems. Okay. So let's see. And this lecture is purely exam oriented, so I'll be not getting into the details and proofs of all these things, because here we cannot expect the proof of all these things. And for the reference book, I am following MD Raisingania book, okay, for integral equations and boundary value problems. You can find it on internet. Now let's see. Yeah, and just let me give you a few more things before solving any kind of integral equation. All we need is Newton-Lineage rule here. So let me mention the rule. Okay, because this will help us most of the time. Okay, to solve Volterra integral equation. Okay, Newton-Lineage rule. I'll be dealing with one variable as well as both the variables. So let us say I have a function, say f of x equal to some integral over, let me take phi 1 of x to some phi 2 of x and then some g of t dt. If I have to differentiate this thing, okay, I have to find out f dash x. Okay. Then this rule says that instead of this t, you'll be taking with g of phi 2 of x into derivative of phi 2 of x minus g of lower limit. It will be phi 1 of x and then derivative of phi 1 of x. This is for one variable. Okay, this is for one variable. When I have just g of t, I was sure that this is a function of t completely. So this will be followed. And when I have a function of two variables, okay, let us say I have a function of two variable. I consider my function to be, say, it is like this: phi 1 of x to phi 2 of x. This is my capital F. Okay, it is of two variables. Say g of x comma, let me not take x in fact. Okay, yeah, even if you take it, no problem. G of x comma t. Okay, and then dx. I have a function like this. Okay, in that case, what do I do? I have to find out f dash x. Okay, here g is a function of x and t both. Okay. Oh, hold a moment. I'm sorry. This is t. When I have a function of this kind, what am I going to do? So in that case, I have to apply Newton-Lineage rule of two variable. So if I have to find out f dash, then it will be first phi 1 of x to phi 2 of x and then partial derivative of this g with respect to x, partial derivative with respect to x of this g plus g xt will remain here. Okay, and first this t will be phi 2 of x and then its derivative, then minus g of lower limit, that is gxt, and this will be taken place at t equal to some phi 1 of x into derivative of phi 1 of x. Okay, let me write it clearly: phi 1 of x derivative. This will be phi 1 dash x. Okay, so now in the next step, this t, at the place of t, I'll be putting this upper limit first. Okay, at the place of t, I'll be putting upper limit phi 2 of x. Okay, phi 2 of x. And then for this thing, I'll be putting t equal to phi 1 of x, and rest everything will remain same. So this is for two variables, f dash. Okay. So these two things will be appreciated for solving a Volterra problem, or sometimes we also we convert Fredholm integral equations into Volterra. Okay, by this changing the limits. Okay, and making the kernel to be piecewise, and then we make it Volterra, and then we again solve it by using Newton-Lenn's rule. Okay, we have got many methods to solve integral equations. We have iterated kernel method, we have resolvent kernel, and then we have got this regular method, Newton-Lenn's rule. So we have got many methods. We will be dealing with basically three methods which are mostly useful. Okay. Now let me take one problem so that you understand the flavor. So let me take one example based on this example. Let f be a continuous and differentiable function on R. Such that f of x equals x square plus integral 0 to x e power minus t, and then f of x minus t dt. All right. So they are asking, what is my f of x? What is this unknown function f of x for which this given equation is true? So let us solve this. Okay. To apply this, I'm sure you must have many basic methods to solve what will be my f of x. So again, let's try by the basic method itself. So consider this f of x equals x square plus integral 0 to x e power minus t, and then f of x minus t dt. See, unless I have this in the function of t, I cannot think of solving anything, because here I should have, if you compare this, then let me compare. So if you compare this, then you are getting something like this. It should be function of t, correct? Here I have f of x minus t. And now let me play a basic game, because this is what you have been doing since childhood. So 0 to x, can I do this? Do I have the liberty of doing? Do I have this liberty of doing this? Okay, and most of you who are confused what I have done, just recall this. Integral 0 to some a f of t dt is nothing but integral 0 to a f of a minus t dt. The most important formula which you have learned in your +2 level. Okay. 0 to a f of t dt is nothing but 0 to a f of a minus t dt. Yeah. Now our integral equation gets simplified and gives us this equation. F of x equals x square plus, what was there behind? 0 to x 0 to x e power minus of x minus t into f of this. X and x will be getting cancelled. This x and x will be getting cancelled, and I'll be just having t. Okay. I'll be having t. So f of t dt. Now we can think of applying Newton-Lenn's formula. So here I see that, okay, this is nothing but a function of two variables here. Okay, function of two variables. Here I have x and t both, so I cannot think of applying just formula number one. I cannot apply this formula most of the time. because here I just have only t, and to apply the formula when I have x and t both, I have to apply this formula, and this is the most used formula. So now let's go for this, and see, this formula looks bigger, okay, but it is not. Once you start practicing these things, this formula will ultimately come into your mind. Okay. At the first time when I was reading, I even got scared and that what is this? But later on when I started practicing these things, so this became a 2 minutes Maggi noodle. So that's all. I can think of differentiating this. So I'll be getting f dash, I'll be going step by step, so please stay with me. F dash x will be equal to, this will be derivative of x square is 2x plus, here I'll be writing the term just for, because I'm doing it for the first time here. So till by del x of whose x minus t, and then f of t dt, then plus power x minus t into f of t. Okay, at what t equals to, my upper limit is x, and then derivative of x is 1, and minus, I'll be doing with the lower limit, so e power minus x minus t, and then f of t, and t equal to 0, and derivative of 0 is 0. So mostly this part will not contribute anything. Okay? This part will not contribute anything. But for the sake of, please make a habit of writing this, because sometimes you may get here cos thing, and whenever there is cos, and if you think that 0 does not contribute, then there will be big trouble, because cos of 0 will give you 1. So please make a habit of writing this every single time whenever you are solving, no matter how smart or how fast you get, still make a habit of writing. Okay, because those who go fast make mistakes, those who go slow, they cannot complete the problem, so you have to be in between. So let's go. I'll think of f dash x equals, this quantity will give me 2x, and let us see what I get from here. Okay, so it will be 0 to x, and now differentiate this quantity. So basically I'll be just getting, if I differentiate, okay, or else if there is some problem, then you can think of even doing this. Let me use different ink. This is nothing but e power x, e power minus x, and then plus t, correct? So I can separate this and write down this. And if I have to differentiate with respect to x, then only this quantity will play the game, and rest of them will be out completely. Okay, rest of them will not contribute anything. So I can think of doing it. Okay, or else I think that I have another method for this, because this will create a problem for me, in fact. So here in this case, I'll go with the usual one, and I'll give you one more formula for this. Okay, you can even get escape of all these things. Okay, it will be a simple problem. If I can minus e power minus 6 out, I can simply think of applying one variable formula. Okay, here I applied 2 because I did not notice the kernel. Okay, so that is kernel was separable, so I could take e power minus x out. Now let's solve this. So if I differentiate, I'll be getting derivative of e power minus x will be e power minus of x minus t, and then f of t dt, and this little coefficient of minus will come out, and I'm done with this. And now let's go for this quantity. So if I put t equal to x, this x minus x will give me 0, and this quantity entire will give me 1, and I just have here f of x, nothing else, and this quantity will contribute 0. Okay, so I'm ready with this. Now let us go. F dash x equal to 2x. Can I take this minus out and completely write down 0 to power x e power minus of x minus t into f of t dt plus my f of x. Now again, if I go on differentiating, I'll not be getting anything, okay, because this part is not going to vanish. So to vanish this thing, I can make a substitution from this equation. Okay, I can make a substitution from this equation, because I see that this quantity, right, the third term will be nothing but, I can write f dash x equals 2x minus this quantity right here will be nothing but f of x minus x square. Okay, f of x minus x square, I can easily say, and then this will be plus f of x, and we can call it from equation 1. Okay, so let us see what I've got. F dash x equals 2x minus what I had, f of x plus x square, f of x plus x square, okay, and then plus f of x plus f of x, and this role of f of x is now over, and this quantity right here will going to give me my desired equation. Okay, I have here f dash x equal to 2x plus x square. Now I'll simply integrate it to find out my f of x. Simplest job is to now integrate it to find out equation. So let's see. I'll integrate this. So I'll be getting f of x equals this quantity right here will give me 2 times integration of x will be x square upon 2, and integration of x square will be x power 3 upon 3 and plus some constant c. Okay. There should be no constant because I do not want a family. I want a complete function of x. So I have to impose one condition. Okay. So to evaluate this constant, we impose a condition. We impose a condition. So what condition can we impose? If you look at the equation, okay. If I say, look at the differential equation, what is given? Yeah, I have here f of x equals x square plus 0 to x e power minus t f of x minus t. What happens if I put here f of 0 equals, okay? So it will be 0, and then from integration 0 to 0, I have here 0. I'm not saying this is the only condition, okay, but this is the most easiest condition that you can use to find out your c, okay, and most of the time you will be getting conditions from here, okay. Which condition to be imposed? So either you can impose it on f or you can impose it on f dash x, but here in this case we have only f dash x, so we cannot think of imposing the condition on f dash, rather we will impose on f. So f of 0 equal to 0, I know it from my differential equation. Sorry, integral equation, not differential. Sorry, it's integral equation. F of 0 equals 0. So I'll impose this condition here. So f of 0 will be equal to this quantity will be 0 and this quantity will be 0 and plus c, which forces c to be 0. So if my c is 0, I easily have my f of x is nothing but x square plus x cube by 3. Okay, this is my required function. This is my required function. So here you solved one problem. Now let me solve one more from CSIR NET, and you can think of applying more. Let me take one more problem from CSIR NET only. So here we go. They're saying here comes the problem. I do not remember the year exactly. They're saying the value of alpha, okay, for which y of x equals 1 plus alpha x is a solution of integral 0 to x e of x minus t and then y of t dt equals x. Okay. So now let me write down the options they have given is 1, then you have minus 1, b, c you have given 2, and d you are given minus 2. Okay. Now let's go to solve this. So again, you have got, now let me rewrite the equation so that it looks good. So x equals integral 0 to x e power x minus t to y of t dt. Okay. Now I know that this y of x equal to 1 plus alpha x is a solution. Okay. I know that this will be my solution. Okay. So that means what? I can either put here 1 plus alpha x and solve this equation. Okay, I can put this and solve the equation. Okay, or I can think of applying some other method and find out the answer. Okay, so here we go. Let's go. I'll differentiate this quantity. I'll be getting here 1 equals partial derivative of e power x minus t dt plus the same quantity e power x minus t and then y of t at t equal to x, and derivative of x is 1, and since this limit is 0 and this is not going to contribute anything, so I'm writing here 0. Okay, because just now I explained you this thing. Okay, when there are this lower limit is 0, it will not contribute anything because ultimately you get its derivative to be 0 and it will be multiplied with the entire quantity. So this quantity will not give you anything. Now let's go. So we have here is 1 equal to integral 0 to x. If you differentiate this with respect to x, I'm sure I'm going to get the same quantity. Okay, e power x minus t into y of t dt. Okay, I'm getting the same quantity. And right here, this if I put t equal to x, then this x minus x will give me 0. So this quantity here becomes 1 and this will be y of x. Okay, so I'm getting just here plus y of x. And I'm stuck over this. So what is this quantity? I can think of making a substitution, and I know that this quantity is nothing but x here. Okay, this quantity is nothing but x here. So I say 1 equal to x plus y of x. Okay, now let me name this equation 1, and I'm using equation 1 here. Okay, so from equation 1, now you say y of x equal to 1 minus x, and they have given the solution is like y of x equal to 1 plus alpha x. So if you compare, you get alpha equal to minus, minus 1. All right, alpha equal to minus 1. So in that case, your B option will be correct. Okay. So that's for today. That's all for today. We will see you in my next video.